In this video, we are going to continue with section 2.4 on shortest distances and closest points, and we are going to do section 2.4.2, the distance between two lines. So there are three kind of possibilities to consider out of the four possible arrangements for two lines in three-dimensional space, and the first here is if the lines are intersecting or coincident. Well, if they're intersecting or coincident, then the shortest distance between them is 0. They touch, right? So the shortest distance between them is no distance at all. If the lines are parallel, well, then there is a fixed and constant distance between them, and we can use a formula that we saw previously. If we simply choose a point P, any point P on one of the lines, let's say line 1, we can do the distance from that point P to L2. So the distance between lines works out to be the same as the distance from a point to a line from point P to L2. And you could do this the other way around as well, right? You could choose a point on L2 and do the distance to L1. It doesn't really matter which way you choose it. The more interesting situation, I guess, or the new situation for us is what happens when the lines are skew. So the lines are skew. Remember, skew lines are non-parallel, non-intersecting lines, so they have distance between them, and they in fact have a minimum distance, which is shown here in our dotted blue line. So the way that we are going to get a handle on that, well, there's a couple of ways of thinking about it. Here is one of them. We are going to join or construct vector p1, p2 out of the points that we can see on each of those lines. And then if I take vectors that you see here, p1, p2, d1, and d2, and if I just rearrange them, so if I take them all and I put them tail to tail, black, so tail to tail, then we have a situation which we're familiar with. You might not see that right away, so why don't I add a little help for you, a little few dotted lines here. So if I add some dotted lines there, maybe some dotted lines here, those three vectors, if I take them and I place them tail to tail, well, they are forming the three adjacent sides of a parallelepiped. And the height that we want, the height of that parallelepiped, right, this height right there, right, a perpendicular height, turns out to be exactly the same height as the distance between those skew lines. So we have this kind of, or this relationship here, that this height h, our distance from line 1 to line 2, is equal to the height of that parallelepiped. So you're going to remember from your unit on vectors that the volume of a parallelepiped is the area of the base times the height. And if we solve for the height, then we're getting the volume divided by the area of the base. And you learned that the volume could be calculated as the absolute value of the triple scalar product, p1, p2, dotted with d1 crossed d2, divided by, well, the area of the base. What's the base? If we look carefully at our diagram, the base is, well, it's that parallelogram right there. And so the area of the base is the norm of the cross product of the vectors that are making up the sides of that parallelogram, and those were vectors d1 and d2. And so the height of our parallelogram is the distance. So there is our distance formula. There's our distance formula in the case that the lines are skew. Now, that's not the only way of thinking about this. Let's just do very quickly another common way of getting this distance formula. So the distance from L1 to L2, well, you can think that this distance, right, this distance here has got to be perpendicular to both lines. And we know that something about vectors that are perpendicular to two vectors at the same time. So the vector that I've drawn in purple has to be perpendicular to D1 and perpendicular to D2. Well, the cross product, D1 crossed with D2, is exactly in that direction. So that gives me the direction of the minimum height. But that doesn't give me the height. That vector could be way too long. It could be way too short. But luckily we have some other information sitting here. If we take P1, P2 and project that back, then this vector here, which is the projection of P1, P2 onto that cross product, onto D1 cross D2, that vector is of the correct length. And if we want the distance, then we want that length of that vector. So another formula, which actually works out to be exactly the same thing if you simplify things a bit, is the norm of the projection of P1, P2 onto the cross product of D1 and D2. So in the next example, we are going to see how to apply this distance from line to line. And so obviously the first thing that we're going to have to do is figure out, before we can give the distance from line to line, which of the cases applies.